Hello colleagues, my name is Phoenix and this is the 7th episode of my SKSE modding tutorial series. In this video I'll continue the discussion about hooks, specifically about the function called hook. This hook works by modifying the binary file so that when a certain function is called, the control flow is transferred to your function. The virtual function hook and the function called hook have a lot in common. In the previous video, I'll talk about plugin compatibility when using a hook of the same virtual function. This is also applicable to the function called hook. Now, I'll explain why these two methods are easy to use, don't require assembly code, and why it's important for the signatures of the original function and your function to match completely. Open the address in IDA. This function determines which target an NPC should choose for battle. Specifically, at this point, it checks if the target can be reached using the check movement function. If the target is inaccessible, a large number is subtracted from the score variable to select another accessible target. But these details are not so important right now. If you have already watched the video about function signatures, you know that these instructions set the values of the arguments RCX, RDX, and XMM2. Then the function itself is called. Here the return value, which is in the rex register, is used. The call instruction performs two tasks. First, it puts the address of the next instruction on the stack so that, when returning from the function, it knows where to return. Then the control flow goes to the beginning of the specified function. Now imagine that instead of this function, the control flow goes to your function. The same return address is on the stack, so by the red instruction in your function, the control flow returns back to this instruction. According to the calling convention, the RCX register is responsible for the first argument. Since the combat controller pointer is in the RCX register at the time of the function call, the first argument of the function is the combat controller pointer. When your function is called at this point, the same value is still be in the RCX register. This means that the first argument of your function is the same combat controller pointer as the first argument of the original function would have contained. This also applies to all other function arguments, even those passed through the stack. For instance, if your function ignores the second argument, unlike the original, its code simply don't read the values of the RDX and XMM1 registers. There is nothing wrong with that. However, if you want to use the third argument of the original function, it should also be third in your function, as at the time of calling your function, it is in the register corresponding to the third argument. If the third argument of the original function is a float, then before calling the original function, the value of the third argument is written to XMM2 register. The R8 register in turn contains an initialized value. Therefore, you can't have an integer third argument and read a value from it in your function. You also cannot write your function with more arguments instead of the function with one argument. Before calling the original function, the calling code initializes only the registers corresponding to the function arguments. Therefore, when you replace the call, the registers and the stack area corresponding to the arguments that the function does not have is also initialized. The same applies to the return value. Your function should return a value of the same type as the original, as the calling code works with the register as if it is the value returned by the original function, unaware of the substitution. Typically, for a hook to work correctly, the signatures of your function and the original function should match. Your function mimics the behavior of the original function following the calling convention. However, there is some flexibility in this rule. You can change the type of arguments and the return type. You might not do this, but for completeness I'll discuss it. According to the calling convention, You cannot replace a float type with an integer, and vice versa, as they are passed through different registers. But what happens when there is integer matching? The calling code assumes that it's placing a value of one type specified in the signature of the original function into the register, and your function reads from this register assuming that it's possibly another type specified in the signature of your function. Initializing the register before calling your function and then reading from it in your function is actually analogous to the reinterpret cast operation. Therefore, the type of argument of your function should not be larger than the type of argument of the original function. Otherwise, initialized data read, which is undefined behavior. Suppose the first argument of the function is a float. In this case, its value is placed in the first 4 bytes of the XMM0 register, and the remaining bytes of this register contains initialized memory. If the first argument of your function is a double, your function expects the first 8 bytes of the XMM0 register to be initialized, and when trying to read from the register, it reads initialized memory. The same logic applies to integer types. If the argument of the original function is an int, the calling code initializes only ECX part of register, or another register corresponding to the argument number. If your function takes an argument of type void pointer, or any other 8-byte type, it operates with the RCX register. This means that your function tries to read the last 4 bytes, which is a defined behavior, as these bytes were not initialized by the calling code. If the type of argument of your function is smaller than that of the original function, your function processes only the lower bytes. Typecasting does not occur in this case too. For example, let the original function takes unsigned int 64 and your function takes unsigned int 32. The calling code sets the value in the RCX register, and your function processes only ECX part. This means that a reinterpret cast has implicitly occurred. For unsigned numbers, this behavior matches the usual typecasting. If the calling code initialized the argument with a large number, its higher bits are cut off, and your function does not know about it. In this context, bool can be considered as a 1-byte unsigned type. As for the truncation of signed types, you can think about it what happens with them. With double and float, things are a bit more complicated. Float uses the first 23 bits for fraction, the next 8 for exponent, and the last bit for sign. Double uses 52 bits for fraction. So, if a function reads float from a register containing double, it reads the last 32 bits of the fraction. That is, there is no typecasting or rounding, which probably won't suit you. If the original function has a return value, you cannot exclude it from your function. However, you can add a return value to your function even if the original function does not return anything. The calling code simply ignores this value. This can be useful if you want to use your function in other parts of your code where you will also use its return value. Since the calling code reads the register set by your function, the rules for return types are reversed. You cannot return a type smaller than the original function, as the calling code reads initialized memory. If you return a type larger, truncation occurs. Thus, at the moment of execution the call instruction, the calling code places all arguments in the corresponding registers and possibly on the stack, in accordance with the calling convention. You can use this by creating a function signature in such a way that the function body can work with these set values as its parameters. This is possible thanks to the calling convention, which defines how the calling code and the original function agree on the location of arguments and the order of working with the stack. As a result, your function can pretend to be the original, and the calling code won't notice this. To achieve this, you can, for example, use the same signature as the original function. Then your function works with those data types that the calling code assumed. If you don't care about a specific argument type, you should at least know its size to avoid reading uninitialized memory or truncating data. The same happens when using a virtual function hook. Before calling a virtual function, the calling code initializes all the registers and allocates the necessary space on the stack. And instead of calling the original function, your function is called. As with the virtual function hook, don't forget to call the original function when it makes sense. As I mentioned in the previous video, you cannot just write a call to your function. Now I'll explain why you have to be tricky. Go to this address. This function launches a spell projectile. It initializes launch data and passes it to this function, which launches a projectile using this data. Usually I don't specify the function address in its name, but this time I did it so you could see the address. Note that the instruction takes up 5 bytes. The first byte, E8, indicates that the next instruction is a relative direct call. The next 4 bytes specify where exactly the function is located. As you can see, these bytes don't look like the function address. That's normal. They indicate how many bytes to move relative to the address of the next instruction. Let's verify this. Here is the address of the next instruction. This offset consists of 4 bytes, which form a number in little endian format. This differs slightly from what you are used to, because the least significant bytes of the number come first here. To convert this number to big endian format, it simply needs to be reversed. This number indicates how many bytes to move relative to the next instruction. By adding this number and the base address, I obtain the address of the launch function. It's even possible to go to this address and confirm it. But what if you need to go in the opposite direction, that is, up relative to the current function? Here, a signed number is actually encoded. A positive offset means a jump down as the value of the IP register increases, and a negative offset means a jump up as the register value decreases. Signed numbers are represented almost the same as unsigned ones. Only weight of the most significant bit is negative. If the most significant bit of the number is 0, this means that the value is positive and the offset is downwards. If the number is negative, the offset is upwards. To determine where the execution flow will be redirected, this number needs to be added to the address of the next instruction. But before that, I'll convert the number to decimal. For this, I'll have to subtract the weight of the last bit, as the calculator considers it positive. Here is what the number to be added looks like, without taking into account the last bit. By subtracting the weight of the last bit, I get a decimal representation of the number. Here is what it would look like in 8-byte hexadecimal notation. To find the address, I add the offset to the instruction address, that is, I subtract the obtained number from the instruction address. You may have already realized that addition and subtraction are the same, and indeed they are. It turns out that to determine the address, it's enough to simply add the instruction address and the offset, ignoring the last carry bit, i.e. overflow. By adding the result without considering this bit to the base address, I get the function address. Thus, the next 4 bytes of the call instruction contains a signed number, offset relative to the next instruction. The computer simply adds it to the address, ignoring the overflow bit, and execution flow goes there. Don't forget about a little endian format. Now you can understand why you cannot just call your function using the same instruction, even if you have calculated the offset correctly. If you haven't guessed yet, let's determine the maximum offset in bytes that can be moved this way. What is the maximum positive signed 4-byte number that can be encoded? It looks like this. That's 2 billion bytes. Sounds like a lot, right? That's so many kilobytes, so many megabytes, and about 2 gigabytes. Almost the same value is available for downward offset. Thus, you cannot jump further than 2 gigabytes. Since your DLL file is located in a random place in RAM, like Skyrim binary itself, the distance between them can be more than 2 gigabytes. This limitation also applies to the GMP instruction. A trampoline can help with this. Imagine that you can change more than 5 bytes. To go to an absolute address, you can write such code. First, you write the runtime address of your function to the RAX register, then call it instead of the original. Since the call instruction puts the return address on the stack and registers will be in a consistent state, just the same after the call instruction for the original function. How many bytes this code take? Here is another website that helps you in addition to Godbolt, especially in the next video. I write code. In the REX register, I write a 64-bit value that takes up the runtime address. So, the move instruction is 8 byte plus 2, call instruction 2 bytes. A total of 12 bytes. That is, if you can change 12 bytes in a row, you can go to your function. A trampoline is a place where you can write this code to make a jump to your function. You could also write something similar. There are many options to jump to your function from trampoline. The function call hook works like this. Instead of call to the original function, you write a call to your trampoline. In the trampoline, you write a long code with jump instruction. Thus, the call instruction saves the return address and redirects the control flow to the trampoline. In the trampoline, a jump to your function occurs. Why doesn't anything break because of the trampoline? After the call instruction, the program is in the same state as after the call instruction to the original function, in the same state as it would be after the call instruction to your function if it were within 2 gigabytes. That is, the registers are set, the return address is on the stack. Then, you initialize it in the RAX register with your value, and then made a jump to your function. After this jump, the stack did not change, only the instruction pointer changed, so the state is still valid. Why won't changing the RAX register break anything? You'll fully understand this in the next video, but I'll explain roughly now. First of all, you know that it's not an argument register, meaning neither the original nor your function read anything from it. This is precisely why you cannot use RCX, RDX, and others. If the calling code saves a local variable in REX, calls the original function, and then continues to use the saved value, your hook overrides this local variable with your function address. After calling your function, this registers holds a different value than the calling code expected. However, there are volatile and non-volatile registers. Any function, even one that returns float or void, may change the value of the rex register as it pleases. Therefore, the calling code mustn't save anything in it before the call, as this data loses after a call. Therefore, calling code before calling the original function saves all the necessary data on the stack or in non-volatile registers, such as RSI and others. Thus, the code with the trampoline may change the rex register, and this do not lead to errors. Notice that in the caller code, the call instruction is used, while in the trampoline memory, the GMP instruction is used. The call instruction in the caller code is necessary to save the correct return address, that is, the address of the instruction in the calling code after the call instruction. The GMP instruction is used in the trampoline memory just to move control flow to your function. There is no call instruction. It won't correspond to any read instruction. The read instruction in your function reads the return address, which was written by the call instruction from the calling code. Thus, to hook a call, you need to jump to your DLL, for which 12 bytes needed. This place is called a trampoline. The function call hook involves making a call to the trampoline instead of a call to the original function, and in the trampoline, a jump to your function. There are several ways to get a trampoline. In Common Leap, one of them is based on allocating memory next to the game memory. I'll show another one, it's much easier to explain. It's called a code cave. Both of these methods can be implemented so that using both is very simple. In Common Leap, this is already implemented. The function call hook is no different from the virtual function hook. Notice that when you hook a function call, you don't change the function itself, you change the function in which this call is located. All other places where this function is called remain untouched, as well as the function itself. Per tradition, I will first show how to perform a function call hook like a hacker, and then I'll show you how it should be done when creating mods. Our goal is to implement a double projectile launch. The plan is simple. Perform a hook of the function call projectile launch, and instead of launching one projectile, launch two, directed in different directions. So let's start writing the hook. I found a code cave that has enough bytes for the trampoline. This is an empty space intended for a landing functions. Note that the start address of the function is divisible by 16. You can write code that finds suitable code cave itself, writes move and jump instructions, and also write a call to the found memory. To help understand what's happening, I'll show the entire process from start to finish. First, modify the call instruction. To do this, you need to calculate the offset. Since the address of the next instruction plus the offset equals the start address of the function, the offset is the start address of the function minus the address of the next instruction. If the jump is upwards, you'll get a negative number. The signed representation is designed so that you can calculate it on a calculator. Just remove the first 4 bytes, there should be F everywhere. Now you can change the call instruction. Using the saveWrite function, set the last 4 bytes to the obtained offset. Since numbers are stored in little endian format, you don't even have to do anything, just write the number. Actually, call offset is assigned for byte type, so you can use int32 and use negative values too. Next, write the code in the trampoline. Use the website again. As you can see, first you need to write 48b8, then the address of your function, again in little endian format, then ffeo. First, I'll write a function that just calls launch. Let's check if everything works. Run cheat engine and go to this address. Visually it's the same, a call function. Press space to jump. You are in the trampoline. Look, here is the end of previous function, and here is the beginning of the next one. Move, jump. Let's see how it looks like during execution. I enter the game, set a breakpoint. I cast a fireball. The breakpoint triggers. Press F8 to move to the next instruction. Press F7 to enter the function. Here you are on the trampoline. You have jumped to your function. Let's start writing the function. It takes two arguments, handle and launch data. The first argument is projectile handle pointer, and the function writes the handle of the created projectile into it. The second argument contains the data necessary for creating a projectile. Despite the fact that the function is a member of the projectile class, it does not have the first argument this, as the function is static. The plan is to launch one projectile slightly to the left and the other slightly to the right. For this, I change the horizontal angle in launch data, launch the projectile, then change the angle again, and launch the projectile once more. Let's check. Everything works as I assumed. This code only works with missile projectiles. Due to how flame and beam projectiles are handled, the game won't launch a second projectile, and also ignores the angle in launch data. Of course, it can be fixed, as you can see in my projectile mod. The same compatibility question arises as in the previous video. What happens if two plugins hook the same place? There is an override and the plugins are incompatible. Last time, I solved this problem by storing the pointer to this function, which I then replaced with mine, and called the original function not directly, but by this pointer. This time, I'll do the same. I've already explained how to calculate the address of the function to which the instruction jumps. You need to add the address of the next instruction to the offset number. I read the number, it's the offset. I add it to the address of the instruction, which is 5 bytes larger than the address of the call instruction. Since I read the offset as int32, I automatically handle both a jump up and a jump down, because, as I said before, this offset is stored in the binary same way as int32. I cast this number to the type of the pointer to the function of the signature that I'm hooking, and remember it. This is the pointer to the original function or potentially to the function of another plugin that hooked this place before us. Everything I said about the original function in the previous video, in particular about how, when and why to call it, also applies to the function call hook. That's why I call the original function as one of the launches. Everything I said in the previous video about compatibility also applies in this case. That's why I called the original function only once. Now I'll demonstrate how this can be done using common lib. It looks almost the same as in the previous video. First, create a class with a static function. Then declare a pointer to the original function. Declare a hook function. Make sure you call the SKSE alloc trampoline function before all hooks with trampolines. This function requests SKSE to allocate some memory for you. In my template, this happens in the load function. The argument is the size of the trampoline you would like to have. There is always enough memory, so I don't recommend you skimp on this function. I always specify 1 KB, and it's always enough. It's unlikely you'll need more, and it's likely you'll need to specify less. Return to the hook function. Apply the function call hook into the trampoline using the write call function. This is a template function pass in the template parameter 5. I'll explain what that means later. The first argument is the address of the hook. I explained how to get it in the video about address library. The second argument is your function, which needs to be called instead of the original one. The return value is a pointer to the original function, or possibly to the function of another plugin that hooked this place before you. I hope you've already understood this from the previous video. Let's check. Here is what it looks like during execution. JetEngine hints at where the call will be made. All functions in this place are game functions, as indicated by SKSE.exe. As well as the call to launch function was the same before you hook. Now, JetEngine couldn't figure out where the call is being made, because it's being made to your trampoline. It's allocated within a 2 GB range relative to the SKRIM binary. This memory belongs to your plugin and was allocated so that you could jump to it using relative offsets. Each write call function, write branch, or kaibiak code are located here. Look, I have a lot of hooks in my test plugin. You'll probably only have single jump to your function here. Remember I talked about the combination of move to racks and jump to racks instruction combination. In Common Lisp, they did it differently too. An absolute jump is written here. Look, it also takes up a lot of bytes. As I said, there are several ways to jump from a trampoline. I told one that, in my opinion, is easier to explain and write. Remember how you used the template parameter 5 in the write call function? This function can also take a template parameter of 6, but no more. Go to this address. This function handles dual attacks by the player. At this point, the start time of the dual attack is obtained using the getTickCount function call. Pay attention to the structure of the call. It takes up 6 bytes, the function itself is displayed in pink, and the KS register is used. Unlike other functions, an indirect absolute call occurs here. The program reads the value located at the specified address and goes to it. This is an imported function. Its code is located in one of the Windows libraries, and at this address in our binary file is the absolute runtime pointer to the start of the function. I think that's all you need to know about such functions. As you probably already understood, when using a hook for their call, you need to use a template parameter of 6, since the function takes up 6 bytes. Usually, you will hook standard functions, but don't forget about this. Remember I mentioned the write branch function? It is necessary for the hook of the call by the jump instruction. Go to this address. This function is called when the NPC decides to block an attack. First, it puts the combat behavior block attack object on the behavior stack, then calls the enter function for this object. Notice that this instruction clears the stack, and this one restores the original value of the non-volatile RPX register. As I've mentioned before, a function mustn't change the value of certain registers, and RPX is one of them. Therefore, it's initially placed on the stack and then restored. The register is used in the function body. Then there is a jump to the function. This is called tail call optimization. Instead of the call instruction, which would be immediately followed by the read instruction, the compiler placed a jump to the function. Its read is the read of this function, and the control flow returns to the calling code of this function. If you want to use a hook for the enter function call, which is actually a jump, you need to use right branch. Whether you use 5 or 6 depends on the size of the instruction itself. It's usually 5. Same as for call instruction, as you already know. As I've mentioned, all the details about the compatibility of such plugins can be found in the previous video. However, there is a new detail to consider. Look at this code. It hooks all calls to the actor combat hit function. Here, here, and here. As you can see from the code, the pointer to the original function is the same for all. The real pointer value depends on the order of calling these three functions. Indeed, initially it's all the same function from the game. However, other plugins may hook only some of these three calls. Suppose there is a plugin that hooks only the call from the actor do mill attack function. This code could potentially call this plugin's function when the projectile combat hit function call is triggered. Moreover, since the code doesn't save two other pointers to the original function, it could potentially do not call the functions of plugin that hooked to these two calls. Note that in the next commit, the author fixed this problem and now saves 3 pointers to the original function and calls them in their corresponding functions. Now the code is compatible. So, to hook a function call, you need to have access to memory within 2 GB of the hook location, which is called a trampoline. You request this memory using the SKSE elect trampoline function, specifying 1 KB as the argument. This function should be called once before all hooks that use trampolines. To hook a function call, just like when hooking a virtual function, you get the function signature, and then in the class, you define your member function with the same signature. Don't forget to save the pointer to the original function and call it by this pointer if this call makes sense. If you are hooking several calls of the same function, you need to save several pointers and call corresponding original function in your corresponding functions. To hook a function call, use the write call function at the address where the call occurs. Firstly, the call to the original function is replaced with a call to your trampoline, and in the trampoline itself, an absolute jump appears to your function in your DLL. Don't forget that sometimes you need to pass template parameter of 6, not 5, and sometimes use write branch function. All this can be done with such simple code thanks to the fact that the calling code prepared the registers and stack for the calling the original function. You use this by writing the function signature in such a way that your function works with this register and stack as with its parameters. That's why a call is written to the trampoline, so that the correct return address is placed on the stack, and in the trampoline itself, GMP, so that only the instruction pointer changes, and nothing more. That is, at the moment the execution of your function begins, the state will be the same as the calling code assumed. Therefore, the code will not even notice the substitution, and after the call, the execution will continue as if nothing had happened. Now I'll demonstrate several examples of using hooks. Remember in the episode about address library, I modified the function code so that the NPC always dodges arrows. I cleared the instruction code responsible for that part of the if statement. As I mentioned before, this method can lead to plugin incompatibility. However, I also mentioned that this can be avoided by hooking the function call that returns the dodge probability. Now you can fix this. Compared to the previous code, only the address and function change. Since my goal is to make the dodge more frequent, I return 1. But you can take into account the presence of certain perks or the skill points and return different values depending on that. I call the original function. It doesn't break the hook logic, but someone else might hook it, not with the intention to change the dodge probability. If someone hooks its call to change the probability, the plugins are logically incompatible. But it don't lead to CTD, and instead the change of the plugin that hooked last take effect. I check this. In fact, the reaction time and movement state also affect the dodge ability. That is, the NPC won't dodge if the projectile is very close to them, or if for some reason they cannot strafe at the moment. But I have definitely eliminated the randomness from this process. Now I'll show how to make NPC not attack if they don't have stamina. For this, there is a function startAttack that randomly selects an attack using the calcAttackChange function. If the NPC doesn't have stamina, the function should return 0, otherwise the original value. You can compare the current stamina of the NPC with the actual amount of stamina spent on the attack. Note that the calcAttack stamina drain function is called nearby. You can get the first argument from the actor using static cast, and the second argument, attack data, is already present in your hook. However, in the original game, stamina costs only apply to power attacks. Therefore, if you compare stamina and attack cost for a regular attack, it is comparison of stamina and 0, and the check always pass. Instead, you can compare the current stamina with 20 for a regular attack and with the actual stamina cost for a power attack. By the way, stamina can become negative in the game, which is why such a condition is used here. It would be incorrect to compare the current stamina with the costs, as in this case, the mechanic with negative stamina would not be taken into account. Now it's time to add stamina cost for regular attack, isn't it? The calc attack stamina drain function is responsible for this. By exploring the code, you can understand how stamina costs for an attack are calculated. If it's a bash, stamina mult is multiplied by the corresponding game setting. If it's a regular attack, the cost is 0. If it's a power attack, the costs are calculated as the weapon weight multiplied by game setting plus game setting multiplied by game setting, apply the mod power attack stamina perks, and then the result is multiplied by stamina mult. The calc attack stamina drain function is used in 4 places. The first place is already familiar to you, choosing an attack by NPC. They don't choose a power attack and their stamina is empty, which also includes the negative stamina case. The second place is a check before playing the animation. The third place is the attack. This is where stamina is drained during the attack. The fourth place of use is unknown for me. Something related to packages? Yeah, procedure use weapon. Unfortunately, there is no place to hook in this function. So you have 2 options. Either hook all 4 calls of this function, or hook the beginning of this function and redirect the execution to your code. Since this episode is about hooking a function call, I choose the first option. In the next video I'll try the second option. You need to hook all 4 calls of this function. For this, create 4 functions and 4 pointers to the original function. And one common function which contains all business logic. This function takes the original value. Note that you've hooked all calls of the calc attack stamina drain function that occurs in the game, but not in your DLL. This means that when your code calls this function to compare the current stamina with the attack costs, it uses the original version of the function, not your version with the hook. If instead you had hooked the beginning of the calc attack stamina drain function, it would have changed the behavior of the function itself. Then, when your code calls calc attack stamina drain, it would have used your version of the function with the hook. You already know the downside, but the upside is that such a hook would be consistent with your previous hook, which prohibited attacking without stamina and also called the calc attack stamina drain function for it. This is consistent because the same function from your DLL is used everywhere. I return 20 for a regular attack and the original value for a power attack or bash. Check-in. Continuing the discussion on stamina, I'll show how to make jumps consume it. There is a function actor jump that first runs series of checks and then executes test action data. If the jump is successful, this code is executed. You need to hook something where there will be this argument. For example, you can hook getScale. The hook of this function call should reduce stamina and then return the original value. You might want to hook the call of jump itself at this point. However, the jump might not perform. For example, these checks don't pass or action don't execute it successfully. In this case, stamina shouldn't decrease, but in your case it would have decreased. That's why I choose this exact place in the code for the hook, as it's executed only upon a successful jump. You could also listen the jump animation event and decrease stamina on it. However, this wouldn't allow you to prohibit the jump if the stamina is 0 or negative. This is where hooks excel over events. You can get more data inside the hook and also influence the course of those events. For example, by hooking the call of the actor jump function itself, you can avoid calling the original function to prohibit the jump. Check-in. There is no delay here, unlike in Papyrus. You can make damage depend on stamina. There is a getDamage function that is used when initializing hit data. You can decrease the damage if there is little stamina. For this, I divide the original value by 2 if the stamina is less than half. Checking. As always, you can check any conditions and change damage as you want. You can create vampirism, health recovery when attacking. There is an actor damage function that calls mod actor value to reduce health when hit. You can hook this call and restore the attacker health, for example, half the damage. Check it. Then you can, for example, check for enchantments on the weapon to activate this code. Thus, you can create a unique enchantment with vampirism. Have you ever had this happen when you weren't the one being punished by mistake? Or vice versa? Let's do it in Skyrim. In the actor do melee attack function, the actor combat hit function is called, which completely handles the hit. The first two parameters of this function are the attacker and the victim. You can clear the actor combat hit call, and then hit won't happen. No effects, damage, nothing, as if the attacker missed. You can also substitute an attacker or a victim. This allows you to implement the mechanics of redirecting damage from yourself to others, or vice versa. It probably is interesting to redirect damage from summons to the owner, so that they live longer, or from owners to summons followers, so that you live longer. I'm implementing the first idea. I get the owner with getCommandInActor function. The same thing can be done for followers. Testing. Now, instead of hitting my Atronach, there is a hit on me. My armor, my resistances, and so on are taken into account. Precisely because the combat hit function handles this internally. If you just want to redirect damage, at this moment you should know what to hook. You can create homing projectiles. There is a projectile move function that handles the movement of the projectile model. This function calls projectile apply gravity, which alters the speed and orientation of the projectile due to gravity. Instead, you can run a homing processing that changes the speed and orientation of the projectile towards the target. Fortunately, the projectile class already has a desired target field, so you don't need to store the current target separately. My plan is to hook two calls. The first hook finds the target and writes it to desired target field, and the second handles the homing. First, create a homing function. You cannot call the original function because it rotates the model and changes the projectile speed according to gravity. The function I'm going to write performs this task instead of the original function. Make sure the projectile is missile and that the desired target field is initialized. Otherwise, you need to call the original function. By exploring the code of the calling function, it can be understood that the v is the vector of the projectile movement for this function call. To maintain the movement speed, it's necessary to keep the length of dv the same, but change its direction to the target. Similarly, linear velocity needs to be changed. Next, a hook needs to be applied somewhere at the beginning of the projectile's life to initialize desired target. For missile projectiles, it's usually empty. I'll hook the moment of the projectile appearance, the call of the launch function, which you've already hooked before. Launch data has target as its field, which is what I initialize. A check for missile again. Then a target needs to be found. The test for each reference function is suitable for this. It calls your function for each loaded refer. I choose the simplest condition. Find the nearest NPC. If such is found, I initialize desired target. Then, I call the original function. It reads the desired target value from launch data and initializes the same field in the projectile. During the iteration process, it's necessary to check that the target is an actor who is not the caster of the projectile, and that it's alive. This implementation can be developed into a complete mod for homing projectiles. Firstly, it's necessary to update the model according to the direction. For simplification, I call a function from my library, and you can study its code if you want to dive into the math. The current implementation is so primitive that the projectile ignores the initial direction and just flies toward the target. It's also worth targeting not get position, but for example the body or head. It would also be useful to anticipate the target's movement and immediately head towards it. I took all these aspects into account in my projectiles mod, and if you're interested you can look at the code. But for the topic of this video, I think you've already done enough. That's all. Congratulations to you. You've made it to the end of the most challenging video I had planned. And I congratulate myself as well. This video was not only the most difficult, but also the most important, as the game calls many functions, each of which can be hooked. If developers take compatibility into account, then each function can be hooked multiple times. This opens up vast opportunities for injecting your code and adding new features to the game. I hope I've helped novice developers gain an understanding of what a hook is, why it works, and how to write it. I hope that thanks to my videos many good mods will be released, in which authors don't just copy the code, but write it with understanding. Understanding is exactly what I strive for in my videos. After all, only when you fully understand what is happening in the game and what exactly you are writing, you can create truly functional modes without bugs. After all, unclear code is always buggy, isn't it? Of course, some parts of some videos may seem difficult to some of you, or even some episodes. Don't worry, if you really have motivation, you will be able to understand everything. You can always return to an unclear moment after a while, and believe me, eventually you will be surprised at what was once unclear to you. Don't forget to ask questions on the RE server. Members will always try to help you there. As for the topics of the following videos, here is a current plan. In the next video, I will talk about incompatible hooks, such as a hook at the beginning of a function, a hook in the middle of a function, callback, and modifying a binary file along with a hook. Then I will talk about tips and tricks that I have collected over these 2.5 years of modding. Then there will be videos about RE, for example how to reverse a structure, how to reverse a function. If you have ideas, share them. With that, I say goodbye to you. Hook Skyrim, enjoy C++. See you in the next video.